Okay, let's begin. So before we begin the topic at hand, which I believe is section 7.8 in your textbook, improper integrals, do you have someone that you want to finish dealing with? Secant x dx via the Weierstrass substitution. Of course, we realized that this was 1 over cosine dx, and by applying the Weierstrass substitution, you would have remembered that cosine is going to be 1 minus u squared over 1 plus u squared, and your dx is going to be 2 over 1 plus u squared du. And this multiplied across kills that thing. We had 2 over 1 minus u squared du, which we had 2 over pretty much 1 minus u times 1 plus u du. And we looked at partial fractions, which was the method that we had right before this. And for this, you could use the cover-up method. U equals 1 makes that 0, so cover that up. Plug in u equals 1, we get 1. U equals minus 1 is going to make this 0, so you cover that up, plug that in, and we get plus 1. And so now we would integrate this. With a substitution, this would have been minus plus which so that could be your integral, right? I thought we left it in expanded form last time, but ultimately, tangent x over 2 was the substitution, and so you had this guy. And that kind of looked different from the formula that we had before, so just to ensure that we had the same thing. So note, if you had the ln of 1 plus tangent x over 2 over 1 minus tangent x over 2. One way you can see that this can be written in more familiar terms. Let's see. We can do that. I want to multiply and divide by something convenient. 1 plus tangent x over 2. At the top, that'll be 1 plus 2 tangent x over 2 plus tangent squared x over 2 over 1 minus tangent squared x over 2. Now 1 plus tangent squared is secant squared, that is secant squared x over 2 plus 2 tangent x over 2. And I know ultimately here, the formula that we know to be correct is ln of secant x plus tangent x. So I think it actually might be convenient to get sines and cosines in there and try to aim for like a cosine over a sine and a sine over a cosine. So let's actually do that. Now, so here I would have 1 over cosine squared x over 2 plus 2 sine x over 2 over cosine of x over 2 over 1 minus sine squared x over 2 or cosine squared x over 2. Multiplying the top and bottom by cosine squared, I would end up with 1 plus 2 sine x over 2 over cosine squared x over 2 minus sine squared x over 2. Double angle formulas tell us that that the denominator is just cosine x. And in the numerator, what can we do here? One plus 2 sine x over 2 cosine x over 2, creating a common denominator in the top. Space. Picking up over here. Now you could also just differentiate this and you'd get the secant, but I want to actually just derive the other formula from this. And this here is actually a trig identity. That will be equals ln of 1 plus sine of x, because that's the double angle formula for sine. And we'd have here the cosine squared x over 2. That would probably be nice to write it in terms of the regular angle, so I'll probably apply another trig identity here. There was an easier way to get here. I can turn that into 2. Now that I'm seeing this, I think there was an easier way to get here. I think there was a nicer way to get here. Hold on. I'm just applying the half angle form identities. But I think I could have used a nicer trig form to get here. And if you see the shortcut, you can let me know. But I'm pretty sure there was a nicer way to get here, which would be a little more obvious. That would be. Yeah, that actually was. Where did we get lost?
I think you made a mistake.
Because I'm getting the answer now that I'm doing this side work.
Like the step, the last step at that part.
Where?
The last line.
The very last line?
Yes. That one should not be over cosine squared x over 2. Like that's just the 1 plus.
Yeah, because if I'm matching this up with that.
Yes, and that's gonna be
This should have been.
secant plus 2 sine.
This is where the mistake
No,
happened, right here.
that one is. That one is.
So this should be a cosine. Okay. So this should have been a cosine multiplied by that. Yeah, I had an extra cosine over there. So picking up from there.
I think you should separate them.
Right, so now when I apply the double angle formulas, the cosine squared minus sine, cosine squared theta minus sine squared theta is actually just cosine of 2 theta. So the denominator now is just cosine x.
And then one.
For the double angle formula for sine, 2 sine theta cosine theta is just sine of 2 theta. So that is just sine x. And so, yeah, now this is ln of 1 over cosine x plus sine x over cosine x, which is ln of secant x plus tangent x, which you know is the answer. You had a little hiccup with the cosine x over 2 there. So that makes sense. Could also differentiate your answer. And you would get secant if you do that. Check if you get secant x, and you would. But that would be how you can, and had I changed to sines and cosines right here, I think I could have even shaved off a couple more steps here. When I was doing that little scratch work, that's what I did just on check. There's something off here. So I just switched the lines and cosines, and I'm like, oh, those 3 lines here actually got me there. So switch the sine over cosine, you can multiply and divide by cosine, it will actually take you to this step pretty quicker than 3 steps. You'll get to here, and then you apply the double angle formulas. that being said, let's move on to, I want to say it's 7.8. It's another section in the textbook. It's more stuff to do with integrals, although it's not directly an integration technique per se. So we've covered all the integration techniques, and we've also covered the strategy for knowing when to apply which technique. So we've done like 7 fundamental integration techniques. And we've gone over when to choose which. And your quiz today is essentially that stuff. So I believe the featured technique on your quiz today is the Weierstrass substitution, because I never really tested you on that. But then I threw in a couple of random integrals to see if you can recognize the strategy to apply. And I think the bonus is about 7.8 stuff, as well as the next section. So 7.8 is talking about improper integrals. So basically this section is going to be kind of a combination of using everything you know about integrals already, as well as everything you know about limits. So you're going to kind of combine those two. Let's talk about that. Now, the fundamental theorem of calculus tells us how to deal with definite integrals. Integral from a to b of f of x dx. Right? But, as you might remember, there were certain assumptions made. Namely, 1, we assumed that f was continuous on AB. 2, we assumed A, B are real numbers, so it's a length of finite space. You want to find the area between this point and that point, you give me the 2 numbers, my function is continuous on that, and then in theory, as long as the Riemann sum integral works out, there are other ways to actually conceptualize an integral, but the way you did it in Calc 1 was using Riemann sums. Assuming that you could actually compute the limit of the Riemann sums, under these conditions, you would be able to calculate that guy, which helps you find the area under the curve. Now, the question is, what if these assumptions fail? Right? So, what if we're not in the situation where your a and b are real numbers and your f is continuous on the interval? Then we obtain what's called an improper integral. So, definition. This integral f to the a f of x dx is improper if 1, f of x is not continuous on AB, and we usually restrict this to finitely many points. So there are a bunch of points where you can pick out where your function is not going to be continuous at those points. Another thing that could potentially cause trouble. What if your b is infinity? So this can happen, and or this can happen, and or what if your a is also not a real number? Perhaps minus infinity, or that can happen. So if your function is either not continuous, or your upper limit is off to infinity, or your lower limit is off to negative infinity, you obtain what's called an improper integral. So examples. So I wrote down a few examples here. I would like you to consider them with me, and then kind of identify if and why they are improper. Did I give you all the, yeah, all of these are improper. So like this integral, this integral, this integral. So these are all examples of improper integrals. Right? These are integrals for which the assumptions under the fundamental theorem of calculus actually don't work, one or several of these assumptions. This is actually a non-example, so this one is not improper. So sometimes it's going to be obvious when you're looking at an improper integral, sometimes it's not going to be so obvious. So looking at A, what would make this improper? How would you know looking at that that that's improper?
Infinity.
The infinity, that's all, right? Once an infinity shows up on an integral, it's an improper integral, like right off the bat. So A is improper because of this, B is improper because of that, E is improper because of those, right? So once there's an infinity, it's automatically improper, regardless of anything else that's going on. Anything else that might make this improper? Yeah?
Whatever x is not continuous is an asymptote.
Yes, but where is the asymptote?
Asymptote is at 0.
Asymptote is at 0.
The y-axis.
This starts at 1 though, so while that is a problem in general, it is not a problem that affects this integral.
Sorry, I didn't mean that particular one.
Oh, good, we're still on it.
Sorry.
So while x equals 0 is an issue, it's not an issue for this integral, so the only issue that this integral has for being improper is the this scenario. Okay. Now, moving on to this one, as you mentioned, of course, automatically when there are infinities, it's improper, but this one has an added problem, right? So there's also a problem, also issue at x equals 0, which is clearly a number between minus infinity and infinity, right? So not only are these limits an issue, but there's a number in between the limits that's an issue, right? Why is this improper?
0.
Right, again, problem at x equals 0. Now, x equals 0 does not show up on the limits, but it is in between the limits. It's on the interval, right? So, because if I'm on an interval and I'm moving from -1 to 1, I'm going to have to pass 0 at some point. Issue?
+2.
Right. X equals 2 issue. This one, this function's an exponential, they're continuous everywhere, so we don't have to worry about that. It's improper because of the infinite limits. This one, same issue as these examples here. X equals 0 is a problem. This one, x equals 5 is a problem. Other than that, it's going to behave. For this one,
1.
and there are others,
-1.
right? X equals 1 or x equals -1 problems. Right? So these guys are improper, and some of them might look quite innocent. It looks like just a regular integral, but on further examination, you'll realize that this has some major issues going on. It has vertical asymptotes at 1 and -1. So does that? How is that going to affect this? Now, it is worth mentioning, this one is a non-example because the issue here is at x equals 0, but 0 is not in the interval 1 to 3. Right? So that's not an improper integral. That is a proper integral. The fundamental theorem of calculus is going to work with that integral, and everything is going to be hunky-dory. In fact, you would know how to integrate that already using the power rule. So, what happens when we encounter an what happens when we encounter an improper integrals? Now there are examples how we know that there are times when you can have infinite limits, for example, and it actually works. Things will actually work out. So it's not automatically true that just because you see an infinity somewhere, somehow there's no reasonable answer, the answer goes off to infinity. Turns out that you can actually get some meaningful, finite answers out of some of these guys. So what happens when you approach them? So we evaluate them, if possible, via this process. Okay, so one, the first thing you want to do when you encounter an improper integral, you are going to identify all the bad points. It's not a technical term, I'm just going to call them bad points. Not all points are bad, you know what I mean, bad points. These are either points where f is undefined, or should we say discontinuous, on a, b, or if a equals negative infinity or b equals infinity. So infinity, positive and negative, there are always going to be quote unquote bad points, as in points where we might have an issue. Other bad points would be points in the interval where f is discontinuous. So first thing you want to do is actually identify what these points are. Second thing, you're going to break up the integrals. If necessary. It might not be necessary to actually break it up. I'll talk about that. To ensure that there is only one bad point per integral. And what do I mean by breaking that up? The fact that using this rule, which you would have seen in calculus 1, if you have a definite integral from a to b, you can actually break that up into the sum of two integrals, right? By taking some intermediate point, say going from a up to c, and then going from c to b, right? We know that this was true. It's actually not that hard to prove from the fundamental theorem of calculus, but that was proven in calc 1, so I'm not going to go over that. So using this, you can break up an integral into multiple integrals, right? You want to break it up so that there's only one bad point per integral. Now, if your integral, as it stands, only has one bad point and it's already exposed, you don't need to actually do this.
Would you do it for like?
I don't want to say and probably expose would be the right thing. Expose. You actually do want to see the any bad points on the integral. So you want to expose one bad point per integral. If there are several, you want to actually flesh them all out. And we'll do some examples of step 2 as well. Step 3. So bad points means f is discontinuous there for some reason. So it's actually an issue to get there, or maybe even infinity. You can't really plug in infinity. There's an issue to be at infinity. So what you can do with these bad points is you can, since you can't really be at those points because your function is either undefined or those points are infinity, what we're going to do is use our trusted old limits. Use limits to approach the bad points. And basically you're going to see how the limits deal with the situation. So if the limit goes off to infinity or the limit does not exist, these are of course situations that you can't get around. But sometimes the limits actually make sense in the sense that they give you a finite answer. So you're going to identify the bad points, you're going to break up the integral to expose the bad points, you're going to use limits to approach the bad points, otherwise evaluate the integrals. As usual, right? Using all the previous techniques that I showed you. So here's an example. Write the breakdowns as described above for. So, I'm going to give you some improper integrals. One to infinity, 1 over x to x, c, 0 to infinity, 1 over x to x, d, 0 to 3, 1 over x minus 2 dx, e, is infinity to infinity, into the x squared dx, minus d2, 1 over x squared dx. Just break these apart to kind of make sure that we fully understand what, well, step 1 and 2 are talking about. A. So first things first, what are the bad points here?
0.
X equals 0. Notice that x equals 0 is not exposed. You want to expose it. So what you can do is to actually break it up. In the sense that now what I can do is I can go from minus 1 up to 0 and then go from 0 to 1. Okay? So on this interval, we're on the interval minus 1 to 1. 0 is here. 0 is the bad point. 0 is the guy that we have to avoid. So what you do is, of course, you break it up into looking at this part where you can't really get to 0, but you're going to want to approach it from the left. And you break it up into this piece, which you can't really get to 0, but you want to approach it from the right. That's kind of the idea, right? And then you kind of inch closer and closer to 0 and see what happens to your integral. Sometimes it'll make sense, sometimes it won't. And I'll talk about what that means and how to talk about that later. But that would be step 2. Okay. So now notice that there is only one bad point per integral, namely 0. He is exposed, and there's no other issues here with 1 over x. Our limits behave otherwise. And so what you would do is, like I said, you want to approach these guys. So this, to apply step 3, use limits to approach. can't be at 0, what you're going to do, say, take the limit as say n approaches 0, and how are you approaching 0? From the left of the integral from -1 up to n 1 over x dx. Okay, so you replace the bad point with some variable, and then you're taking limits to allow that variable to approach the bad point. Plus, you're going to do the same thing with every other integral. Now, with each different integral, you want to consider a whole different limit. You don't mix and match, so you use a whole different variable actually. So you take the limit as say m approaches 0, this time from the right, because we're on this leg, of the integral from m up to 1 over x dx. Now what you would do is, for a while, you'd evaluate the integral all by itself. Step 4. We'll do that later. Right now I just want you to get used to breaking things down. But eventually how you'd follow up on this is, first you ignore the limit for a while, you'll evaluate this guy using the fundamental theorem of calculus and then any integration technique you know, and then you'll get an answer with n in it. Then that expression, you're going to take the limit. And you might get a meaningful answer, you might not. Okay, what's the next one I'm going to break down as? So, bad point?
Infinity.
Oh, it's infinity, right? So 2, what's the breakdown going to look like?
Limit of.
Well, when I say break up, I mean if you need to split it. In this case, because that's the only bad point he's already exposed, you don't really need to split anything. So nothing's going to change there. And now 3, when you're talking about use limits, so you can say the limit, let's say n approaches infinity. Of course, you're not going to do it from the right or the left. You can only approach infinity from the left. So this is 1 up to n of 1 over x dx. What about this one? Bad points?
0 and infinity.
Right, x equals 0 and infinity. So there are 2 bad points. Notice that they're both on one integral. You can't deal with 2 of them at the same time. You can only deal with 1 because we only have the limits from one-sided. 2, you're going to do the breakup.
Could you choose any point in between?
You can choose any point in between as long as it's not a bad point. So what do you want to pick?
1.
1.
Yeah, so you can do 0 to 1 plus 1 to infinity. Right? 0 is the bad point here. Infinity is the bad point there. These are all bad points that exist for this problem, and now I have only one of them per integral. So what I'm going to do here is to use the limits to approach the bad point, and I would pretty much get the limit as say n approaches 0 from the right of n up to 1 of 1 over x, plus the limit as say m approach infinity of 1 up to m of 1 over x dx. Bad points here.
3.
2.
3, it would have, with the 3 there, it's correct that 3 was a bad point, but we had 2 here. So 2 is the bad point. How are you going to break this up?
From 0 to 2, and then 2 to 3.
indicate limits approaching 2. So for this one, you want to approach 2 from the left side. And for this one, you want to approach 2 from the right side. So those would be what the first 3 steps in one of these problem types would look like. Without me doing the whole blue writing. But in your mind, this is what you're thinking. What are the bad points? How am I going to break it up? How am I going to apply the limits? E, how would you break up E? The
Zero.
Huh? You want to put 0 in the middle, so what is it going to look like? What's it going to look like here?
Negative infinity to 0.
Yeah. Now, of course, infinity is the bad point here. So you take a limit approaching infinity, say n approaches negative infinity. N approaches positive infinity. Okay, the last one, F. Do that on your own, tell me what the answer is. Oh, that guy got broken up. So do that. These are examples for next time. I want you to try these, which we'll get through them next time, but I actually want you to attempt these, see how it would go. So that way you'll be aware of whatever issues you might be having, potentially any misunderstandings there are. Sometimes it's hard to identify those where you're just in a class following along. So actually try to get to an answer, or just justify the fact that an answer isn't possible here. Like the limits aren't going to work out, or something is going to be an issue. How'd you break this up? Yeah.
So first I took the integral from -2 to -1 of 1 over x squared minus 1.
Mm-hmm.
And then I took it from -1 to 0.
Mm-hmm.
And then I took it from 0 to 1, and then 1 to 2.
Right. So Did everyone get the same thing?
Why would you go?
So your breakdown should have 4 integrals in it. Now, if what you tried doesn't have 4 integrals, it means there's something you misunderstood about step 3. Yeah.
Might be a dumb question, but why would you go to 0?
Well, how did you think of breaking it up before?
Well, I wasn't too sure, but I did -2 to -1.
Yeah?
Then I did. I guess why I might have been wrong with -1 to 1. I didn't think that.
And then?
It went from 1 to 2. I only got 3, so that's why I'm saying I might have done it wrong.
Right, so the issue was you have 2 bad points. So step 3 says you only need 1 bad point.
Okay.
So
you
it
can have both
means
the same one.
this could be an okay first step, but the middle integral still has an issue.
Okay.
It has 2 bad points, so you want to break that down into 2 separate ones. So he just throws a random point in between them like 0. So he broke that down further into that.
Makes sense.
Right. So it's you want just 1 bad issue per integral, because you can't have a limit. Limits don't go in 2 directions at the same time. You only have to either approach from the left or the right. Yeah. So this is a breakdown of 4. And of course you'd apply a limit here to approach this, a limit here to approach that, limit here to approach that, limit here to approach that, using all different letters. And then you evaluate them. So try that for these guys. See if any other issues are there. That will we'll get through those tonight. Sorry.